Today's episode is sponsored by DL Chemical. They sell a range of polybutenes as well as ethylene propylene copolymers, which are called D-polybutene and D-cinol. Now, I'm actually more familiar with the D-cinol range, where I've used DS600 and DS1100 in a range of industrial gear oils. I've actually been really impressed by how well they incorporate into PAO fluids, especially considering how thick they are. But they've also got really high viscosity index, which can contribute a lot to your formulation. And overall, I've been really impressed with their oxidation stability in service as well. Considering how large the molecule is, they seem to be really shear stable. So if you're looking for an alternate to a very heavy PAO, give them a try. G'day everyone, welcome to Lubrication Experts. And today I have a returning guest, so back by popular demand, Mr. Jack Zakarian. So obviously formerly of Chevron, and did a section on base oils now a couple of months ago, which was very well received, and people have been clamoring for Jack to come back. So now today we're going to actually dive into a topic where it seems on the surface to be extremely basic, but I can almost guarantee that everyone listening or watching will learn something. Now, for all the people who are podcast listeners, we're actually going to be talking through a slide deck today. So there's a lot of visuals that go along with it. So if anyone is exclusively a podcast listener, I would encourage you to watch this particular one on YouTube, because there's going to be a lot more visuals than usual. Jack is going to be talking us through viscosity index. So this is like, one of the most fundamental concepts that we have in our business, right next to viscosity being the thickness of oil. Really, we're just talking about how does viscosity change with temperature. But you might be surprised to learn a little bit about the history of viscosity index and maybe where the viscosity index kind of falls down a little bit. So with that introduction, I'd also like to introduce Jack. Welcome back on the podcast. And
Thanks,
really
Rafe.
good.
Okay, so what I want to do today is talk about, as Rafe said, understanding viscosity index, which is ASTM D2270 as far as a formal method. And the viscosity index, as Rafe mentioned, is something that seems extremely basic. It's been around for 95 years now, and nobody even thinks about it. But when I was a young engineer just starting work at Chevron Research Company, and this was back in 1979, my first assignment was to do all of the pilot plant research and development for a new lubricating oil plant that Chevron was building in California. And so it was known as RLOP, the Richmond Lube Oil Plant. And this was the world's first all hydroprocessing scheme to manufacture lubricants. So I was doing all of the pilot plant work, especially lube hydrocracking. And in the course of all my experiments, we always noticed, and this was well known in the field at the time, that when you hydrocracked a feedstock to make lubes, the highest boiling cut you took from your product always had a much higher VI than the lowest boiling. So if you were trying to make a light neutral and a heavy neutral base oil from the same feed, you would have to overprocess the heavy in order to get the light oil to have a VI that met specification. So as a young, ignorant engineer, I started asking questions about, well, how is this VI calculated? Why is it that this behavior occurs in hydrocrackers? And the more I dug into it, the more fascinating it became. And I learned an awful lot of stuff that I'd like to share with you today on how viscosity index really works. So let me advance the slide. So the objectives. I want to show people how was the VI scale actually created, and then it was modified extensively over the years. I want to educate people about limitations of this method, because it does have the potential for a lot of misinterpretation, and it's not really all that it's advertised to be. And finally, to alert the lubricants industry that there are large economic penalties which are incurred if you follow the current VI scale. So To get down to the definition as it was originally proposed, in 1929, two researchers, Dean and Davis, at Standard Oil in New Jersey, which now is ExxonMobil, they proposed this system, which essentially was a single number that you could use to designate the rate of change of viscosity with temperature. So it's kind of what we call a relative ranking. Um, what you do for a relative ranking is you compare the oil you want to rate against two other oils, one which was a good oil and one which was a poor oil. And so what you do is you have to define these series of oils, and then you can use that to compare your unknown oil and get a number. And so the original definition, Dean and Davis took two different crude oils for the high and the low series, and they distilled it into what we call the narrow boiling range cuts. So you had very light cuts all the way up to very heavy. And each cut from a Pennsylvania crude was designated as the H series, which was high VI, and that was just assigned a VI of 100. And then it was well known at the time that oils from Louisiana Gulf Coast, essentially they were naphthenic character, that those oils had very poor viscosity temperature behavior. And so they got a crude from down there, designated that as the L or low series, and that was assigned a VI of 0. So what I'm going to show on the next slide is I took the original data, which was in Saybolt universal viscosity seconds and degrees Fahrenheit, and I converted it to modern units. And this shows what how VI is calculated. So if you can see my cursor, X is the oil, XY, those are the points we want to calculate VI for. So X would be the viscosity at 100, Y is the viscosity at 40. So if you have an oil at those two viscosities, you compare it to what we call the H and the L series. So these blue triangles, that's the high viscosity index series, VI of 100. These red squares are the low viscosity series. So with this particular oil, you always look at, you do the comparison at 100 degrees Celsius. So it's maybe about 11 centistokes here. So if your unknown oil has a vis of 11, you look at what the high series is at 11, the vis at 40, and then you look at the low series, what the vis at 40 there is. And essentially you use this formula, which is just the difference from here to here divided by the difference from there to there times 100. So if this point is halfway between, the VI is 50. If the point is down here, the VI is 0. If it's here, VI is 100. And anything down here, if your vis at 40 is lower than about 95 or so, any vis's lower than that give you a VI greater than 100. So again, this was everything that went into the original definition of VI. Now, that definition has an awful lot of deficiencies, which I'll get into now. The first thing is that there was very limited reference oil data. From that slide earlier, you can see that at 100 degrees, the viscosity only went from 6.8 to about 21 centistokes. That's fairly narrow for the range of lubricants we produce today. Also, at that time, lower viscosity oils were not typically used. One, because they didn't have much additive technology then, and lower vis oils couldn't protect equipment that well. And also, at that time, the Saybolt viscometers were not accurate below about 7 centistokes. And this was because you were dropping oil through a tube and trying to measure it with a stopwatch. And the thinner the oil got, the harder that procedure becomes. And finally, the H and L series come together very closely as vis decreases. And so, in fact, let me go back to this previous slide. You can see down here, as vis gets low, these lines eventually end up crossing each other. And that makes the calculation of VI for anything in the 6 centistoke and below range at 100. That's a very difficult calculation. It's prone to a lot of error. And finally, to top everything off, when Dean and Davis decided to extrapolate their curve of the original data, they used a second order polynomial to curve fit the data, and that was a huge mistake. Although at that time, before computers and calculators, it was easier to do polynomial fits than it was to do exponential or logarithmic fits. So right away, people noticed that VI needed to be modified to account for some of these things I've already mentioned. And so one of the first things that happened was there were more accurate viscometers. And so they remeasured H and L series viscosities for lower vis ranges. They also found that they didn't have the original crude samples left in their laboratories. So they got new crude, which was still from Pennsylvania and Gulf Coast, but it turned out that the new samples didn't really follow the curve fit of the original samples. And so in 1940, they decided to readjust the data, and they developed another second order polynomial to cover the low viscosity range. Now, getting more to inconsistency. So now after those changes, 1932 and 1940, you had the following situation. There was a region which is essentially higher vis, above 7.3, and that was defined by a set of a parabolic equation that fit the original data. The region in the low vis area was defined by a different parabolic equation. And then finally, there was a region in between, and they just did a graphical interpretation and defined the data that way. If you actually look at the current ASTM method, if you want to calculate VI yourself and do it by the calculation method that is recommended, there are 16 different second order polynomial equations that describe the reference series, which is kind of crazy that you need 16 different equations to describe one line. This chart here actually came from my early days at Chevron, probably from 1980, when I was trying to convince people in the company that the VI scale was messed up, and nobody would believe me, and they didn't want to listen to it. But what this chart shows is if you take the data that Dean and Davis distilled and you plotted it on log scale. So down here we have the vis at 100 on a log scale, the vis at 40. You actually got very straight lines. Don't show the individual data points, but take my word for it that this region up here in the 1929 data is a nice straight line. Then when you look at the 1940 data, that's a nice straight line. But if you took the high vis data and extrapolated it, that's this dotted line, what you see is that the extrapolation does not agree with what the new equation said. So there's an inconsistency on defining VI. Low vis oils below 4 centisoke, actually below about 6.5 or 7, those oils end up getting underrated in VI compared to oils of higher vis, and we'll get into that later. So more inconsistencies, and this is kind of amazing. If the VI was above 130 and you looked at curves of constant VI, so here's 100 Fahrenheit, 210 Fahrenheit, if you plot your data from doing the calculations, it turns out that curves for VI, constant VI, have these humps in them. So what that means is that you can have an oil of 200 VI and it can have this vis over here. It can also have that vis over there. So that's obviously a completely inconsistent situation. This is a direct result of using second order polynomials. If you remember your high school algebra, polynomials are going to have an inflection point somewhere, and basically you're seeing that inflection here. And so when you do that kind of curve fitting, you've got to be careful if you want to extrapolate. And so this situation got so bad as oils improved during Second World War and after. More oils and synthetics were getting these crazy high VIs. ASTM had to do something about it. So in 1964, they made a fix to the scale. So the old D567 became the current D2270. But they made these lines straight, but in order to make them straight, what they did was they had it follow the line for 100 VI, and the 100 VI line, as I've already shown, was also warped. And so all they did was preserve the original inconsistency, but at least they got rid of the curves. So people early on recognized that maybe there's a better way to define VI. So at Penn State College, Fensky and a number of coworkers, they had a great petroleum research lab there at Penn State. They decided to take a bunch of oils from Pennsylvania crude and distill them to try to define the new high VI reference series. So they actually had 230 different oils, and they covered a huge viscosity range, much better than Dean and Davis did, all the way from 3 centistokes to 180. They also took a low VI series, and they took Sugarland crude from I think it's Louisiana, I'm not even sure. It might be Texas, but they took a low VI crude and did 19 cuts of that to define the zero series. And they also recognized then that log-log equations work a lot better to describe the reference oils. So what I'm showing here is if you look at what Fensky did, that's all these red points here. He expanded the scale quite a bit, and I don't show how far out it goes, but it goes, like I said, up to about 180 centistokes. That fits very well on a log vis at 40 versus a log vis at 100 plot. I've superimposed on the Fensky data the original Dean and Davis data. Remember, they only had 7 data points, and it actually fits pretty well. So you would say, wow, the new Fensky high VI series really matches the original high VI series. And when you look at the low VI series, it's a reasonably good fit. There's a little deviation as you get into the higher vises, but basically you would say the zero VI series seems to match. However, there are some problems. And one is the fundamental assumption of VI was that VI is supposed to be independent of the actual viscosity. So if you took oil that came from one crude and you separated that oil into different boiling fractions, every piece should have the same VI. That was the original assumption. Well, if you look at the Fensky L series, the VIs that you would calculate went from minus 33 to 28 if you used the original ASTM method. So obviously, taking a series of oils from one crude didn't give you the fundamental assumption, which was the VI was the same for every cut. Also, the H series, even though it looked very similar to the original Dean and Davis series, it also does not follow the fundamental assumption. And I'm showing this on this next slide. So this slide shows the calculated ASTM VI versus the viscosity of Fensky's 100 VI Pennsylvania crude oil series. And I cut this off at 6 centistokes, but if you continue this 6 all the way out to 180 centistokes, what you find is that all of Fenske's oils cluster around 100 VI. The problem occurs when you get to about 5.5 centistokes. Anything below that, the ASTM VI gives you very low numbers. So an oil that's supposed to be 100 by definition, the reference 100, by ASTM calculation ends up being much lower than 100. And this is highly significant. What you can see is that at 5.5 centistokes, if you're 100, if you make a 4 centistoke oil, you might be down to 80. And this explained my hydrocracking results when I was that young pilot plant researcher, because the light neutrals are in this 4 centistoke range, the medium neutrals are about here, and the heavy neutrals are much further out. And heavy neutral always had a higher VI than medium, which had a higher VI than light. And it actually had nothing to do with the hydrocracking. It was how you measured VI. And that was a huge revelation. So why even bother with getting into all of this? Because we've had the method for 95 years and it seems to work and nobody seems to question anything. Well, the question is the key word, that VI is so widely used that it's accepted without question in many commercial transactions. And that can lead to some misunderstandings about the quality and the vis temperature behavior you're really getting when you purchase oils based on VI alone. Also, VI is used as a quality indicator. And so if low oils are being underrated, that's saying those oils are low quality, when actually you'll see later, they're actually higher quality on a viscosity temperature basis compared to the higher vis oils. And I've already mentioned this, that in the previous slide, difference between 4 and 6 centistoke. The 4 centistoke oil is rated at 83, the 6 is 100. That means that this 4 centistoke oil is considered inferior in quality. And that was the problem I was having with the light neutral I made from the hydrocrackers. People said, no, you have to get a higher VI. It's not good enough. And I kept trying to tell people, no, that 83 is meaningless. This oil is much better than the 83 indicates. And finally, API group classifications are on the basis of VI, and that affects guidelines that you use for lots of approval testing, especially in the engine oil area and read across. And so you're making decisions about what tests to run or to not run based on VI, and VI has been shown here to be an inconsistent measure. So economic incentive. Well, this first thing, and this is something I experienced firsthand, and it came out in the design of our lube plant and every lube plant that's operating now. If you want to produce a low viscosity oil that has higher than 95 VI, you have to over process the oil, because low viscosity will give you low VI, and you can process oil and you might get a medium neutral that's 100, but your light neutral will be 85. So you have to process the 85 up to 100. That moves the medium neutral from 100 up to about 115. So that actually results in a loss of yield, loss of oil, because you're processing, in the course of processing, you lose lubricant base stock. And that totals many, many millions of dollars a year based on current processing. Also, and this is maybe getting more recognized now, but if you have a group 3 or a group 4 manufacturing scheme, what you'll notice is that the low vis oils, the 2, 3 centistoke cuts, and even the 4 centistoke, they always have a lower VI than the counterparts that are higher vis. And this actually reduces their market value, which is an unnecessary reduction. So If we want to improve the scale, what should we look for? Well, the first thing is let's find an underlying principle which is scientifically based. So you could look at viscosity temperature plots, look at the slope of those plots. That gives you a true rating of viscosity versus temperature. Or you could go back to defining a reference oil series, but it has to be well defined and not a patchwork of different sets of data that were gathered at different times. Uh, the new scale should not underrate low vis oils, and it should not overrate high vis oils. I'm not going to get into it on this talk, but high viscosity oils actually, on the current method, have a much higher VI than they deserve based on their viscosity temperature properties. And preferably, what you want to do with a new scale is be somewhat similar to the current scale, at least for oils in the range of 5.5 to 35 centistoke, which was where a lot of the original scale was built. And then we want to reclassify low viscosity oils from group 3 processes as truly group 3, not group 2s, which is the current procedure. So I don't have time in this talk, but there have been a lot of attempts to improve the scale. Back in the 60s, ASTM did an awful lot of work. In the 50s, they had a bunch of symposia with lots of papers presented. And bottom line is nothing has stuck or been accepted. I've done a lot of work myself, and I'm just showing here some of the papers and presentations that I've given if you want to get into more details on ways to improve the scale. I've tried lots of different things, and so far it's been very difficult to come up with a commercially acceptable solution. And so one thing that could be done, and this is the very simple approach, if you remember the slide from Fensky and his high VI oils, when you got below 6 centistokes, you had kind of a linear drop off on the VI rating. And so you could actually just use that slide and say, okay, if the oil is less than 5.5 centistokes at 100, we can describe what I call the VI penalty by a very simple equation. You take minus 12 times the vis at 100 plus 66, and that describes that line where ASTM VI underrates the actual Fensky 100 VI. And so on the table on the right, I'm showing what happens if you just did this simple calculation here. And let me focus, first I'll focus, since I'm an old Chevron guy, on the Chevron Group 2 neutral oils. What you see is that the 100 neutral that's made commercially by Chevron for centistoke, it has a VI of 102 by ASTM. If you use the penalty equation, it should be 119. For the 220, since it's like right in the middle, it basically has no penalty. And also the 600R is higher vis, and again, it's higher than 5.5, so it has no penalty. But the message is that low vis oils are actually better in VI behavior than high vis. Let's go down here and let's look at next base. Next base is group 3. They make a 2 centistoke oil, a 3, 4.3, 5.1, 5.9. So the 2.2 oil comes out with a VI rating of 90. And if you use the penalty equation, it should be 130. So these two oils here, both the 2 and 3 centistoke by next base, they come from a group 3 process, but they don't have greater than 120 VI. Neste is running their plant to make sure the 4 centistoke is at least 120. In the process of doing that, they end up with 111 and 90 for the light cuts. But if you actually apply the correction, those oils are much higher VI than ASTM would rate them. So again, this is highly significant for commercial operation today. So in summary, hard to believe, but this year is actually the 95th birthday of the VI scale. And I hope maybe in the next 5 years, I might be able to come up with something to make a significant improvement, but we'll keep our fingers crossed. The VI has served the industry well. I mean, as I mentioned, it's unquestionably accepted and used pretty much daily in the lubricants business, but it does suffer from fundamental problems that I've pointed out. The scale has evolved and the most egregious problems have been fixed. The way they were fixed was kind of patchwork, but at least they were fixed, and there are still major problems that remain. And the biggest one is the current scale unfairly penalizes lower vis oils. And these days, the lower vis oils are where it's at when it comes to transportation lubricants, both engine oils, transmission lubes, axle oils. Everybody's looking for better fuel economy. They're looking for lower vis oils. To make those lower vises, we have to over process in order to get what's considered an acceptable VI. And that just means you lose oil in the course of doing the processing. One thing I've found, and this is kind of a major issue to design a new scale, is that most people in the past and present have said we want to try to maintain some connection to the current system. Well, the problem is we're trying to invent a rational system which retains the familiarity of the current irrational system. And so that is a tough nut to crack. At some point, people are just going to have to accept that VIs of the old days really are totally different than what they should be. That's the only way we'll actually ever get a new, more rational system. So that does it.
There we go. So, so thanks, Jack, for what was a very kind of like illuminating run through of viscosity
Yeah, it's
index.
more than you ever wanted to know about VI, probably.
Yeah.
Yeah.
So, funnily enough, the way that this kind of podcast came about was it was probably about 18 months ago. I realized in the course of building some training materials that I didn't actually understand viscosity index,
Yeah.
and kind of did a deep dive onto the history and started seeking out people in the industry who actually understood it. And what I quickly discovered was that no one could explain viscosity index
Yeah.
outside of
Yeah.
this is what it is at 40, this is what it is at 100, and this is how it changes.
Yeah.
Now, funnily enough, I have come across a couple of professionals who have done this types of deep dives, and Jack's name had come up on a couple of papers. And so that's kind of where I wanted to do this, because I think this is one of those things in our industry which does not get questioned. And
Yeah.
there's a few
Yeah.
instances in our industry where we have, I think, some underlying assumptions that never people seem to never return to the first principles. And there's value in questioning why we do things the way we do. And one of the things that jumped out to me from your presentation is the fact that we are kind of like losing yield as a result of this kind of
Yeah.
artificial
Yeah.
construct that we've built. And at some stage, right, whether we like it or not, ESG criteria and carbon credits are coming for everyone in the industry in some way,
Right.
shape, or form. And if we can show that by changing an arbitrary scale, we can reduce our consumption of oil, I think that's going to be, potentially the push that the industry needs, right, to get this fixed. Because to date, everyone's just been comfortable with the let's say the irrational scale, as you put it, that we have,
Yeah. Yeah.
and everyone just sort of works around it. So, yeah, Jack, look, really appreciate you doing the deep dive and the hard legwork on on viscosity index and the history and ways to remedy it. I think from my perspective, when evaluating the performance of base oils and lubricants, I'm just going to use your correction factor. That for me, that seems good enough in the
Yeah.
meantime. And
Yeah. That's definitely the simplest thing to do. And as I showed, if you used Fensky series for 100 and 0, there's a lot more data there, and it was more rationally, devised. And the Fensky series, has that drop off. So it's very evident that there's
Mm.
something wrong. And yeah, that correction, at least it gets you started. Um, there are still some issues. I've tried to use the Fensky series to redefine VI. And actually, I think my STLE presentation got into that, but it doesn't quite do the job. And so it's very hard. And part of that is because we're trying to stay at least in the same neighborhood of VIs that we currently are. And yeah, so you could just go back and just adopt Fensky, but by using the correction, that's essentially what you're doing.
Yeah, yeah, no, that's some great insight. So Jack, the thing that we love to do on this podcast is nerd out about what are seemingly inconsequential details, but details that actually have great import and great consequence. So,
Yeah,
really appreciate you shining a light on this particular very, very niche corner of our industry that is both niche and broad at the same time, right? Because there's very few people that have an interest in it, but it affects almost everyone in our industry.
yeah. Well, I can tell you one humor story from my early days at Chevron. So once I got into this VI thing, which I mean, I spent a lot of time in the library sifting through old musty journals and pulled out everything that was written on it. Um, I made a proposal at a major meeting on the uh, just before we were launching our lube plant. We are getting the design finalized, and I basically presented this thing to management and said, our target VI for our oils was 95 minimum. And I told him, I said, we should make 85 or 90 the minimum for the light neutral. And the manager of our process planning group just got up and he slammed the table and he said, a spec is a spec. He goes, we can't do, the whole industry is using 95. He says, we can't do that. And I said, no, if you take our light oil and you blend it with a heavier oil, which is done then in engine oils, the VI jumps up because now you're in a different vis range. And I tried to convince them that we could make the oil with a lower VI, but no one would go for it. And this again just kind of illustrates the thing of when you don't question anything, you just keep doing things the same old, same old. And that had major, major implications for our plant design. And
Yeah.
but a spec is a spec, and I always remember it because later on, when I became a manager of product development, you know, we had to make the spec no matter whether the spec was meaningful or not. And there are a lot of OEM specs that are not very meaningful, but they are a spec.
Yep. Yeah. Yeah. I think OEM specs are potentially another topic for another podcast. So, no, Jack, really appreciate you taking the time to discuss this with us, and yeah, would love to have you back soon.
Okay, great. Well, thanks for having me, Rafe. I enjoyed it and like to keep spreading the message.
Awesome.